This video is on organic analysis. And we only have one aim in this video, is to identify organic functional groups using chemical tests. Although this video is going quite a long one, because there's a lot of different functional groups that you come across in Chem 4, and you have to be able to tell the examiner how you would test for those. If you had two test tubes of two different compounds, you need to know what you do to those to see what they were. So first let's start off with what the different functional groups are, and that's really where you should start when you're answering questions on these. You need to identify the functional group that's in the compound. And what I would do is always draw, if you've got a molecular formula, or a structural formula is what they usually give you, always draw out and display it, because I find it easier to work out what they are then, especially if you've got alcohols. It's easier to work out whether they're tertiary, primary or secondary if you've drawn them out. So we've got the different groups are alkenes, and that's where you've got a C-C double bond in there, a haloalkane, so that's where you've got a carbon attached to a chlorine or a bromine or an iodine. We've got alcohols, that's where you've got a carbon attached to a hydroxide group, a C with an OH attached to it. Remember, you can have secondary, tertiary and primary alcohols, and you've got to use different, well, it's the same test, but you can see different things for them. Aldehydes, you've got, sorry I spelled that wrong, there we are, and that's where you have a C double bond with an H on it. We've got carboxylic acids, and so you've got C double bond O with an OH, and that would be COOH in a structural formula, and an aldehyde would be CHO in a structural formula. And then you've got acyl chlorides, which would be C double bond O with a Cl on it, or you'd see that as COCl in a structural formula. Now it's important to realise that if you've got any of these attached to anything else, then you can use the same test. So for example, if you had a benzene ring, and then you had a C double bond O OH, that would still that could still be tested for with a carboxylic acid test. So don't be put off by this benzene ring. You're always just looking at the functional groups when you're looking for what to do to test them. So we'll start with alcohols. So you can have different types of alcohols. You've got a primary alcohol, which is where you've got an OH group attached to a C that has at least two H's attached to it. So that's a primary. You've got a secondary alcohol, which is where you've got an OH attached to an H, an OH attached to a C which has only one H attached to it, and then you have a tertiary alcohol, secondary, and you have a tertiary alcohol, which is where you've got an OH attached to a C that has no H attached to it. And tertiary. And basically, the way you test for alcohols is you oxidize them. A primary alcohol will oxidize, a secondary alcohol will oxidize, but a tertiary alcohol will not. So that's the first test. If you know you've got a tertiary alcohol or a secondary alcohol, then you can add potassium dichromate, which is acidified. You have to add acidified potassium dichromate, and it will go from orange to green. If you've got a primary alcohol and a secondary alcohol, then you'd have to do an extra test. So you could, if you wanted to, oxidize both of them under reflux. So you'd use acidified potassium dichromate to oxidize a primary alcohol all the way to a carboxylic acid, and a secondary alcohol to a ketone, and then you do the carboxylic acid test, which is coming up later. Basically, you add sodium carbonate and see if it fizzes. So the test is add acidified potassium dichromate, and for primary or secondary alcohols it'll go from orange to green, and for a tertiary alcohol there will be no change, it will stay orange, because the tertiary alcohol won't get oxidized, and therefore the acidified potassium dichromate will not get reduced. Next we've got if we've got a mixture of a ketone and aldehyde, or if you've got an aldehyde and you want to test for that. So remember, a ketone is comes about if you oxidize a secondary alcohol, and it's a C with C's either side and a double bond O. So carbonyl with C's either side, and an aldehyde is a carbonyl group with an H on it. And basically the difference between these is that an aldehyde can be oxidized further and a ketone cannot. And what you use for that is either Tollens reagent, or you use Fehling's solution. For both of these you get no change for a ketone, but for Tollens reagent, for an aldehyde you get a silver mirror, not a silver precipitate, a silver mirror, and for Fehling's solution you get a brick red precipitate. So both of those observations are if you have an aldehyde, but you see nothing if you've got a ketone. Neither of these will do anything with a ketone, so you put no visible change. Then we come to acyl chlorides. So an acyl chloride is if you've got a C-double bond O, a carbonyl group with a Cl attached to it, and basically if you add water to this, so if you add water you will get white steamy fumes of HCl, which will then turn in universal indicator paper red or litmus paper red. Then we come to optical isomers, which I didn't discuss at the beginning because these are organic tests, but optical isomers, they may ask you what you have to do to test between those. And basically optical isomers are ones with a chiral carbon in the middle, so a carbon attached to 4 different groups. So for example you might have CH3, H, Cl and Br around a carbon, and then the mirror image of that will be the following. And to identify between those, you shine plain polarized light on them. And the two enantiomers, these are called enantiomers, if you remember from the optical isomers video. Enantiomers will rotate light in opposite directions. So that's the distinguish between optical isomers. We then come to carboxylic acids, and carboxylic acids are usually something that stumps people in an exam. And what you've got to remember is that it is an acid. And if you add, so this bit here, C-double-bond-O-OH, if you add sodium hydrogen carbonate to this, it will fizz. Carbon dioxide will be given off because it will react if it's basically an acid and base reaction. So you add NaHCO3, sodium hydrogen carbonate, and that will fizz because carbon dioxide is given off. We then come to alkenes, which are something we learn about how we test for in year 10 when you do C1. And basically, the double bond in an alkene, if you add bromine water, will come out and attack it, and you'll get a dibromo compound where the bromine has attached to the double bond. This bromine water is orange, but this thing over here, this compound over here, is colourless. So you can either say it changes from orange to colourless, or you can say it decolorizes. You can't say it goes clear because it's clear in the first place. Clear basically means you can see through it. You've got to say it's either colourless or that the bromine water decolorizes. Finally, we come to haloalkanes. So this is either if you've got a carbon attached to a Cl, a carbon attached to a bromine, and a carbon attached to iodine, and for all of these you can add silver nitrate, as if you're testing for a halide ion. Carbon attached to chlorine will give a white precipitate. If you've got bromine in there, you'll get a cream precipitate. And if you've got iodine in there, you get a yellow precipitate. All because you make silver chloride, silver bromide, and silver iodide, respectively. Then remember that silver chloride will dissolve in dilute ammonia, and silver bromide will dilute in concentrated ammonia. So this white precipitate here would dissolve in dilute ammonia, and this cream precipitate here would dissolve in concentrated ammonia. This yellow precipitate dissolves in neither. So that's an extra way you can see what you've got after you've added the silver nitrate. So let's have a look at a few past exam questions. So here we've got two compounds we've got to distinguish between. So notice they're usually worth about 3 marks, because basically they give you 1 mark for what the reagent is that you choose, 1 mark for what will happen with E, and 1 mark for what will happen with F. So the first thing we want to do is just work out what these two things are. So we've got here an ester. So we've got a carbon attached to an oxygen, attached to a carbon. So that's an ester group. And we've got here a carboxylic acid group, acetyl bond OOH. So if you remember back, the thing that will react there is the carboxylic acid. So we will add NaHCO3, sodium hydrogen carbonate. E will have no reaction, or there'll be no visible change, and F will fizz. It's as simple as that. So here's another example. So here we've got a CCC with a double bond O in the middle, so that's a ketone group, and here we've got CCCl double bond in the middle, so that is an acyl chloride. Remember, the ketone doesn't really do anything, you can't oxidize it any further, so that will always be the no visible change. So we've got to think what the acyl chloride will do, and if you remember, we add water, and with G, no visible change, and with the acyl chloride, steamy white fumes of HCl given off. So this is the final one I'm going to run through with you. So here you can see we've got 2 alcohols. They've both got OH groups on them, no other functional groups. J is a primary alcohol because it's attached to a C that's attached to 2 H's. K, however, is a tertiary alcohol because it's an OH attached to just carbons. There's no hydrogens attached to the C. So that means that J will oxidize and K will not. And so what we'll add here is acidified potassium dichromate. And you must make sure that you put this word acidified, because otherwise you won't get the mark. J will go orange to green, that's what you'd observe. So you start off orange and it would change to green because the alcohol's being oxidized, therefore the dichromate's being reduced, and that forms a green colour. K will have no visible change. Another thing that sometimes people forget is to say which compound they're talking about when they talk about the change. So make sure you put that in. That would be a silly mistake to make if you didn't. If you've got any other questions about organic analysis, please let me know via email.